For example, if I have x squared times x to the 11th, that is the same as x times x, because that's what x squared is, times x 4, 5, 6, 7, 8, 9, 10, 11. So if I count up how many x's I have, that gives me x to the 13th. And I already showed you why it works, because really x squared is just x times x, and x to the 11th power would be x times itself 11 times. So if I multiply all of those together, now I have x times itself 13 times. So I just took my 2 plus my 11 power. So to evaluate that, you actually have to multiply 3 by itself 5 times. So 3 times 3 is 9, times 3 times 3 is 9 more, times 3. You get 243. So 3 to the 5th power is equal to 243. 2 to the 3rd power squared. So what this really means is on the inside of my parentheses, I have 2 times 2 times 2, because I'm taking 2 and multiplying it by itself 3 times. And then I'm going to square that, which means that I have to do 2 times 2 times 2 times itself, 2 times 2 times 2. And when you simplify this or evaluate it, 2 times 2 is 4, times 2 is 8. So 8 times 8, which is 64. Now, if you notice, 2 cubed gives me 3 2's, and I have that 2 times. So if we have a power of a power, what you do is you take the exponents and you multiply them, 2 to the 6th. So if I have x to the 3rd, y to the 4th, and I'm raising that to the 5th power, you have to multiply the exponents of everything. So this is the same as x to the 15th and y to the 20th. And I can show you why. So x cubed, once again, is x times x times x. And y to the 4th is y 2, 3, 4. So I have this 5 times. So that is why you multiply the exponents. So if you want to write this down, when you raise a power to a power, you multiply the exponents. Well, x to the 6th divided by x squared. What we're going to do is we're going to rewrite this so that you can understand why it makes sense, and then you'll write the rule down. So x to the 6th is x times x times x times x times x times x. Divided by x squared is x times x. Now, because we are multiplying everything, we can do some canceling, because I'm multiplying everything on top and everything on bottom. And we're multiplying everything that has the same base. So if I have x on top and x on bottom, x divided by x is 1, so they cancel out. And here I have x divided by x is 1, so that cancels out, which leaves me with x to the 4th in my numerator. So let's do an example of it flipped. So if I had x squared divided by x to the 6th, that would be the same as x times 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 x, right? 6 x's. So once again, those still cancel out, which leaves me with a 1 on the top and x to the 4th on the bottom. So if you noticed, when we have these exponents, I take the exponents from the top and I subtract the exponents from the bottom, and that will give me my final answer. So another way that you could write this is also x to the negative 4th, but in a video just a little bit down the ways, you're going to find out why when we rewrite x to the negative 4 as 1 over x to the 4th, A, that they are equivalent, and B, we typically like to take negative exponents and make them positive. There's always a party with the bigger number. So up here, there's a party because there's 6 people. These two people in the basement, they don't want to hang out there. So so you always start subtracting kind of by where the bigger number is. So 6 minus 2 gives me x to the fourth. Now here, you would do the same thing, but the party's in the basement. There's more people down there. So when you subtract, you do 6 minus 2, and you get 4, but the party stays in the basement. The next property of exponents that we're going to talk about is the zero property of exponents. And what we're going to do is we're going to use what we just learned about quotients to help us figure this out. So for example, if I have 3 to the third power divided by 3 to the third power, I know that I'm going to subtract my exponents, right? That gives me 3 to the 0 power. However, anything to the 0 power is equal to 1. And I'm going to show you why that is true. So 3 to the third power is the same as 3 times 3 times 3 divided by 3 to the third power, which is 3 times 3 times 3. Well, whenever I divide a number by itself, that is equal to 1. Which is why it always cancels out, because when you multiply 1 by anything, you just get 1. So 3 divided by 3 is 1. 3 divided by 3 is 1. 3 divided by 3 is 1. So when I multiply this all together, I get 1. Good luck.
Is that when you have a base raised to a negative exponent, that is simply going to be equal to 1 over that base raised to the positive exponent. And the contrary is, if you have a negative exponent on your denominator, we can make that positive by writing it now as a positive exponent or a positive power in the numerator. Because let's take a look at it. If I was going to follow the quotient rule, that would be what? 3 to the first minus 3, right? If you were to apply the quotient rule, Ashley, if you were to apply the quotient rule, you would take 3, the top numerator, which is this power, and you'd subtract it from the degree or the power in the denominator. So 1 minus 3 is what? What's 1 minus 3? Negative 2. All right? But if now when we follow our negative exponent rule, when you have 3 to the negative 2, we write that as 1 over 3 squared. So do you guys see how if I write it out, I get 1 over 3 squared. If I follow the quotient property, I get a 3 to the negative squared. And then I apply the negative exponent rule, and I rewrite that as 1 over 3 squared, which, like Mendoka wanted to simplify to, we can just simply write as 1 over 9. All right? But all I want you guys to understand is when you have a negative exponent, you have to make sure that if the negative exponent's in the numerator, you write it down in your denominator, and you can create it, and you can show it as positive. And then Sadiq, the other way is if you have it in your denominator, you can write it back up as your numerator.
Okay, so today we are going to go back and talk a little bit about radicals. So radicals are like square root, cube root, fourth root, fifth root, etc. So when we have a power, in order to undo or solve a power, we use radicals. So a power would be like a to the nth power equals b. And if we are going to change that into a radical, we would take the nth root of b, and that would give me n. And that totally makes sense if you think about it in terms of something that you're familiar with, like something squared. So for example, if I have 6 squared equals 36, if I was going to solve this and I didn't know what 6 was, so let's say instead of 6, it was an x. In order to do this, I would take the square root of both sides, and that would tell me that x is equal to 6. So for what we're doing today, it's okay if you only give me positive square roots. However, technically, the square root of 36 is 6 or negative 6, right? Because 6 times 6 is 36, and negative 6 times negative 6 is also 36. All right, so now we're going to do a little bit of practice with numbers that are not just when our n value is not just 2. So really quickly, if you want to write this down, you can label it. So this is your index, and the index matches your exponent. This is called the radicand. So it's what you're taking the root of. And then the symbol itself is called the radical. The vocabulary isn't as important as understanding the process. So let's do a few example problems. And if you ever have any questions, just let me know. Okie doke. So let's look at this problem really quickly. If we are multiplying underneath our radical symbol, we can break it up and make it a multiplication problem separately. So you can rewrite this as the square root of 81 times the square root of x to the 4th. So when we have the square root, it might be easiest for you to do the prime factorization of a number and find groups of 2. However, I hope that you already know that the square root of 81 is 9. And over here, what I'm really asking myself is what times itself is equal to x to the 4th. So I hope that you know that x squared times x squared equals x to the 4th. Since there are 2 of them, they no longer need to be underneath the square root. So we can take it out, and our final answer is 9x squared. Okay, well, let's do one that's a little bit different. We'll do a cube root one. So let's say we have 24x to the 5th. Now, because my index is 3, in order to take it out of the radical symbol, I need to have 3 of them. So let's start with 24. So if I look at 24, 24 is the same. Well, let's break it up into 2 pieces first. We'll break it up into the number and then the variable, and then we'll do a little bit more. So this is the same as the cube root of 24 times the cube root of x to the 5th. So let's start with our number. 24 is the same as the cube root of 6 times the cube root of 4. Let's keep breaking it down. The cube root of 6 is the same as the cube root of 3 times the cube root of 2. These are both prime numbers, so I'm done. Let's break this down. The cube root of 2 times the cube root of 2. Now here I have the cube root of 2, the cube root of 2, and the cube root of 2. Because I have it 3 times, that means if I multiply it by itself 3 times, I can take out the 2. It's out of jail. It is no longer underneath the cube root symbol. However, cube root of 3 is still going to be in my final answer. So right now I know that I have 2 times the cube root of 3. And then let's look at these x's. I'm going to switch colors hopefully to help you see better. So the cube root of x to the 5th is the same as the cube root of x times x, 3, 4, 5. Okay? So when I do that, do you see how I have 3 here, which means I can take 1 out, and I'm left with 2 underneath my cube root, so x squared. So my final answer is 2x times the cube root of 3x squared. I'm going to do one more example, and then you guys have some practice problems. Okay? Okay, so just like when we had when we had a radical and we had a bunch of things being multiplied by each other and we broke it down, you can do the same thing when you're dividing. So as long as you're only dividing or multiplying, you can split some things up. So I can rewrite this as the 4th root of x to the 4th divided by the 4th root of 81. So I am going to do the top part in red. The 4th root of x to the 4th is x times x times x times x. There are 4 of them. My index is 4. That means I can take 1x out. Now I am going to do prime factorization of 81. So when I do that, 81 is the same as 9 times 9. 9 is not a prime number, so I'm going to break it down even more. 9 is the same as 3 times 3. 9 is the same as 3 times 3. I have 4 of them, since my index is 4. The 4th root of 81 is the same as 3. So my final answer is x over 3. Now, technically, the 4th root of 81 could also be -3, but we're only going to focus on positive values when we have even roots. But technically, -3 times -3 times -3 times -3 is also equal to 81. Okay? You have some practice problems, and there's a few at the end with solving using radicals, but I feel like you guys are pretty good at that. If you have questions or need extra help, just let me know. Okay? Good luck.